So we so what how does one proceed in terms of calculating the or connecting pressure drop versus volumetric flow rate when the fluid is flowing through pipes which are connected in series. Now let us look at the other configuration that comes or that one often encounters is when pipes are connected in parallel. So let us take an example. So let us say you have a fluid that is entering the pipe, and let us say it is divided into 3 parts. Okay, so the pipe is divided into 3 parts. Okay, so let us call the first one pipe 1, pipe 2 and pipe 3. All of them let us say have a length L, and let the diameter be different. So let us say this is D1, this is D2 and then this is D3, and fluid or flow rate Q is coming. So, it's the flow, there is a fluid that is entering that junction, the flow rate is Q, and then it is passing in through 3 tubes before joining again and coming out. So, this is the configuration that you have, and your interest is to connect the relation between Q and pressure drop. So, let us say Q1, Q2, Q3 are the flow rates through each of the pipes, and let us say H1, H2, H3 are the head losses through each of the pipes. So, again you can take the same analogy as we saw in case of pipes connected in series, that the volumetric flow rate, it is like your current, the pressure losses, the head losses is like your voltage. So, you can see that the current should be divided into 3, while the voltage across the section should remain same. In other words, in this particular configuration, H1 should be equal to H2 is equal to H3. In other words, the pressure drop across the inlet and the outlet will be same whether you take pass 1, 2 or 3. However, the flow rate, the total Q should be divided into Q1 plus Q2 plus Q3, just the fact that the volumetric flow rate will be divided into 3 parts and going in. So, these are the 2 rules that will dictate the flow configuration in this system. Now, we could ask the question, given H, can you determine Q? So, let us say you have got a particular pump. So, you know that it has got a certain head loss associated with it, and then you are interested in finding out what is the maximum flow rate that you can pump through this system. Now, you could write down the relations. You can say that H1 is F1 into let us say L1 by D1 into V1 square by 2G, H2 is equal to F2 L2 by D2 V2 square by 2G, H3 equal to F3 L3 by D3 V3 square by 2G. Now, so this is how you would calculate H1, H2 and H3, but we do not know what is H. We know H1, H2, H3, but we do not know V1, V2, V3, but that is simple because actually if you look at it, since H1 is given, we need to just calculate V1, but to calculate V1 you need to know what is F1, and F1 of course depends upon the Reynolds number, and Reynolds number again depends on V1. So, there is no simple way to calculate it except that you have to assume value for V1, calculate a Reynolds number, or let us say calculate Reynolds number, calculate F1, and then see whether that F1 is consistent with V1, or in other words you have to calculate a V1 and F1 that is consistent with each other, that can give you a major head loss that is given by H1, because H1 is prescribed in the problem. Note I am specifying H. So, H is equal to H1 equal to H2 equal to H3. So, that means we know H1, we know H2, we know H3, we do not know V1, V2 or V3 are unknowns, and our idea is to calculate V1, V2, V3, but we need F1, F2, F3, which are all functions of Reynolds number, okay, which are in turn functions of V1, V2, V3. So, this is really a nonlinear equation. So, you assume a value of V1, calculate the Reynolds number, calculate F1, okay, and see whether that F1 is actually for the Reynolds number that you have calculated, and this procedure can be repeated. Or the another way of doing it is to start by looking at a value of F1. You could also do this, assume F1. So, since you know H1, calculate V1, then calculate Reynolds number, and then calculate F and see whether it matches with the F1 you have assumed. If not, correct it, and so on, and this might be probably a better way of doing things. Either way you can do, either you start by assuming F1 and calculate V1, or start by assuming V1 and calculate F1 and continue that procedures till you get a prescription. And you have to do the same thing for H2 or rather V2, and you can do the same thing for V3, and then you can calculate V1, V2, V3. So, this is the procedure to evaluate the flow rate through a parallel connection if H is given. You could also ask the reverse question: given Q, can you estimate H? So, what are the things that we know? H is given by H1 plus H2, sorry, H is equal to H1 equal to H2 equal to H3. Q is equal to Q1 plus Q2 plus Q3. We know H1 is F1 into L1 by D1 into V1 square by 2G. H2 is F2 into L2 by D2 into V2 square by 2G. H3 equal to F3 into L3 by D3 V3 square by 2G. This I can rewrite as F1 into L1 by D1 into V1, that is Q1 divided by A1 square. So, because if I divide flow rate with area, I am going to get velocity. This is F2 L2 by D2 into Q2 by A2 whole square. This is F3 L3 by D3 Q3 by A3 whole square. Then I can write, so this expression tells me that I can write Q1 is equal to H1, okay, divided by L1 by D1, and then you have 1 by A1 square to the power 1 by 2. So, I am just calculating Q1 from the expression. So, I have got H1 and F1 into F1 into L1 by D1 into 1 by A1 square, that is going to be my Q1. Similarly, I am going to get an expression for Q2 is going to be simply H2 by F2 into L2 by D2 into 1 by A2 square to the power 1 by 2, and I will also get an expression for Q3 in a similar fashion. Then if I substitute here, I will write Q is equal to the expression for Q1, which is really H divided by F1 into L1 by D1 into 1 by A1 square to the power of 1 by 2 plus H2 by F2 into L2 by D2 into 1 by A2 square to the power of 1 by 2 plus H3 by F3 into L3 by D3 into 1 by A3 square to the power of 1 by 2. But we know that H1, H2, H3 are equal, therefore I will write Q is equal to H to the power of half into 1 divided by F1 L1 by D1 1 by A1 square to the power of half plus 1 by F2 L2 by D2 1 by A2 square to the power of half plus 1 by F3 L3 by D3 1 by A3 square to the power of half. So, what I have done really is that I have now gotten a connection between Q and H. Okay. So, our problem originally was that given Q, can you estimate H? So, by manipulating the expressions, we have got an expression between Q and H. Again we have a problem because we do not know what is F1, F2 and F3 are. So, the only way one can do is that assume F1, F2, F3 given so what is the question, given Q. Given Q, calculate H from the above expression. Okay. So, but we do not know whether F1, F2, F3 are right, but we have calculated H, but we know that H is same as H1 same as F into L1 by D1 into V1 square by 2G. Okay. So, that means you can now calculate V1, because in this expression you know H1, you have assumed F1. So, you can calculate V1. Similarly, from H2, H3 calculate V2, V3, and if you know V1, V2, V3, you also know Q1, Q2, Q3, and if you know Q1, Q2, Q3, you know that Q1 plus Q2 plus Q3 should be equal to Q given. If not, then go back and change F1, F2, F3 there and repeat the procedure. So, this is an iterative procedure, and this iterative procedure needs to be done because there is no other way to solve these expressions. So, you can start by assuming F1, F2, F3, then you can calculate a Q from that. Sorry, given the Q, you can calculate an H from that, and then you can calculate V1, V2, V3 and calculate again, see whether the V1, V2, V3 that you get is balancing your constraint Q1 plus Q2 plus Q3 equal to 0. So, let me tell that again. We start by assuming F1, F2, F3, then we use the expression connecting Q and H to calculate H, and since we know H, you can use the individual expressions like H1 equal to F1 L1 by D1 V1 square by 2G, those expressions to calculate V1, which means you can calculate Q1, Q2, Q3, and then you can check the constraint whether Q1 plus Q2 plus Q3 is given to be the total flow rate, and this procedure can be repeated. So, this is just one way of doing it. Essentially what you have is a system of equations and you need to solve them, and it is your choice really whichever way you want to do it. This is just one really algorithm for that. Okay. So, now given that, so we have seen how one should think about when pipes are connected in series, how should one think about when pipes are connected in parallel. You could also have junctions. So, let us look at a case where you have junctions, you can have elevations. So, so far we basically said we are going to look at pipes that are all horizontally aligned, and therefore, there was no elevation change.